talented data scientists, and welcome to a nice little introduction on polynomials. All right, so why do we use polynomials? Well, quite simply, if we have a data set which looks, once we plot it, looks as follows, you'll see that linear regression is quite a nice example to use to be able to predict values later on. However, not all data looks like that, unfortunately. So you can see if we look at the shape of this particular data, trying to do a linear regression to be able to predict results later on isn't really going to work. However, a polynomial, which allows us to change shape, we can actually make it fit in quite nicely there, and then we can predict results along the red line. So, for instance, if we had to say, well, x equals 1, we can then predict that it's going to be, around about 2.5. Okay, whereas we'll get a totally wrong result with the linear regression. All right, so the formula is basically that we'll always have a constant term. Now, a little bit later on, you'll see that we actually swap all of these around. We start with the x squared, work down to the x of 1, and then down to the constant term. But there's always a constant term. Then we just divide, we plus a number multiplied by x, and then a different number multiplied by x squared. Then it might be another number multiplied by x cubed, etc. So we can have as many terms as we want in the polynomial. Now, the amount of terms that we have here is also known as the degree of the polynomial. All right, let's see now those formulas in action. So if we have a look at this, remember I said to you we kind of swap it around. So it's the, you can see here we're timesing x plus a by x, and then we're adding on the constant, and you can see this is known as a linear polynomial, so pretty much the same as what we have with linear regression, and it's just ax plus b. All right, and b, by the way, is the intercept that we have here on the y-axis, so you can see here it would be -1. All right, if we now have a quadratic will always start with a squared, then we just times it by bx without just to the 1, the power of 1, and then again we add our constant term. So here the constant term would be -1, 2, 3, 4, but you can see there it's ax squared plus bx plus c, and this is known as a quadratic, and it always has this kind of sort of shape to it. Okay, so you actually get to know polynomials and their shapes, and quadratics always have this kind of shape to it. Whereas a cubic, okay, again, it always has this sort of shape to it. And this time we start with ax cubed plus bx squared plus cx plus d. All right, and obviously we can go on, hey? So we can go to the power of 4 to the power of 5. And again, these are known as the degrees of the polynomial. So you get to know the shapes quite well as you're working with them. And then just keep in mind that you start with, for the quadratic, you start with a 2. With a cubic, you start with a 3, and so on. So an important point to remember now is that if you have a look at your biggest exponent, and you -1 from it, so in this case it's 2 minus 1, that's going to be the amount of turning points that the polynomial has. So if you look here, our greatest exponent is 3, so -1 gives us 2, and you can see there's 2 turns in the polynomial. So if we went on to, had a polynomial that started on ax5, there would be 4 turns in the data that would actually occur. Great, so now what we need to do is take our data set and plot it, but we need to go and find what's the right polynomial that's actually going to fit the shape of our data. You can see here we're underfitting. We've got a straight line, and it's not a great fit. Here we've got a fit that's just right, and look at our data points, and you can see if we use our polynomial to predict a particular value of x and what its y will be, it's going to have quite a nice shape to it. Overfitting, you can see here the degrees, because as you go up in degrees, it'll actually kind of fit the shape of your data more, but you get to a point where it's called overfitting. It's just going up and down, and you're not going to get actually a good predictive result out of this particular polynomial over here. Okay, so that's known as fitting the polynomial to the data, and we will deal with that later. So if we have a look here, if we have a polynomial here, x squared plus x squared plus 4x, or x squared plus 6x, you can see we're increasing the size of the coefficient. So if you take each of these x values, and for instance, you just plug it into the formula, you'll get that result. If you take this x-axis value, at least, and you plug it into that formula, there's your result. So you'll end up with these shapes over here, and you can see that as you change the coefficient, it actually changes where that coefficient, or that polynomial at least, is situated. And you can see if we go from 4 to 6, it moves the whole polynomial sort of down and to the left. So naturally, whether you do pluses or minuses and what those coefficients are will have an impact of how the polynomial gets placed. So again, being able to predict the right polynomial to shape our data is something that we will deal with later. So there is a great tool called Desmond. All right, and on Desmond, what I've done is gone and plotted a bit of data here. Now, I've gone and just put on a few polynomials above where I plotted the data. And let's have a look at the first one. So this is linear, quadratic, and a cubic. So if I go and had to plot a linear, you'll see, oh, it's not a great fit for the data at all. Can't do much prediction over here using this particular polynomial. So let's turn that one off, and let's see if the quadratic helps us. So we know that a quadratic is always going to have this sort of U shape, and yes, we do get a few predictions over there, but again, it's not great anywhere else, and we're kind of going to sort of come up with totally the wrong result. You can see if we've got a value of 1, we're going to end up down there, whereas we sort of need to be up here somewhere. So let's turn the quadratic off and we turn on the cubic, and there we go. We have a polynomial that has followed our shape quite nicely and allows us to predict values. So for any x, we're able to predict a y value quite nicely on this particular polynomial. All right, so hopefully that has given you quite a nice little introduction into polynomials, and we will see you in the next chapter.